Hey Ruby people, hey Python people, hey JavaScripters. Have you ever thought like, what does it sound like if you listen to a server from the inside? You know this talk is going to be about a stateful application server, but first to wake you up, since this is the last talk, I found a nice song on the internet, and it just reminds me how fun it is to work with stateful application servers. Okay, you kind of got an impression what it's like. So my talk will go through three things. First, you will know the requirements of the game we've built the server for. Then, like what are the ideas? How do we develop the whole thing? And lastly, let's just wrapping it up. So, what are the requirements of our game? I'm working at Wooga. This is a social gaming company, and we have built a stateful application server due to that requirements. So that's why I want to show them to you first. The first requirement, which is really important, is we have intense, short-lived sessions. You can imagine like this, that a social game, as you know it today, is almost every click is an action, and users come and go within 5 minutes. So there's a lot of fluctuation going on. So another requirement we have at Wooga is scale. We plan for about 1 million DAU, and that's how we start the whole application. It may outgrow that number. And that's not the first game Wooga builds. So we have the advantage, and that's kind of a requirement, or that's a setting we have, that the simultaneous users is predictable. That's pretty nice. So we know kind of like existing games have this kind of DAU, and we can expect this kind of simultaneous users. And therefore also, we can assume that the load the application will hit, even at peak DAU, will be finite. We don't have to scale infinitely. That's a very good point. And also, deployment, very easy thing, but no service interruptions. And this is very special to stateful application servers, as you will see. And one point I really like, and which I think is very important, it's good night's sleep. You know, at Wooga, we as developers are responsible for the whole system. And if monitoring triggers an alert, there's a call chain. At the end of the call chain, there's a CTO. So if we screw up as developers, if our application doesn't respond anymore, and we don't respond to our phones, we are in just big trouble. Okay, so I set up a good night's sleep prayer to give you some perspective what we had in mind building this server. Dear science, we want to understand our system, and to achieve understanding, let us grow the system step by step. Let the spirit of Rich Hickey live through us to our application. So I'm aiming for simplicity. Now you kind of know the setting, what we're into. Let's meet those requirements. So you heard about this intense, short-lived sessions. Imagine someone playing and doing a lot of clicks. And we had the idea, many updates are done faster when they're done in memory. And the second idea was, many small actions are better sent in batches. So then we don't have connection overheads. Like, let's look into that. So what you can see here is output from our log. it's a sequence of commands. Somebody starts a quest, upgrades a building, finishes that, levels up in the meantime. That's the actions you can imagine for a user we have. And to avoid HTTP overhead, those actions are batched. So we just pack those 6 actions into one HTTP request. And as you will see, there's no magic involved. It's a quite straightforward system. We have a batch execute call, which behaves like any command. We're putting the whole batched commands into an array, into the JSON body of the post request, and then process them in the server sequentially. If we step further into our system, here you can see we're using Cuba, by the way. It's a nice little micro framework for Ruby. Besides the with block, which is ensuring us thread safety for what we do within the session, I'll show you later, each batch do name method params. It's quite forward. We go through this array, iterate over each batch, and just execute the actions the user requested from us. And to give you some perspective on how our application actually looks like, here's some commands and how we implemented them. And also, this kind of refers to the good night's sleep I promoted before. We just want to write idiomatic, beautiful Ruby code that speaks to us whenever we read it back. And this quest command is a good example. It's quite straightforward. Start sequence, starts a new quest. That's it. Upgrade command, very small. Which is like, basically, you can imagine a command for us is like a controller, which is assembling the stuff our models have to do within one command. Level up. This is also a very good example. You can see that we have to do many, many tiny little modifications to the game state within one command. And also, this is like undermines the idea. It's very good to have a stateful application server, therefore, because those things can be done faster when you just directly change stuff in memory. So how did we meet scale? The other requirement we had. And we just thought, as long as all active sessions fit into memory, I think we're good. And as always said, let's go shopping. And first, you need to know that at Wooga, we host our systems. Each team hosts its own kind of infrastructure. Everybody is free to rent any server he wants. Even if someone would buy hardware, that would be OK. So we went out and just took those beefy servers, 32 cores, 32 gigs of RAM, SSDs, 2 gigabit network card, amazing peering and CDM backend. So we have the upscale is quite high, and it's really good. We can use that. And scaling out. So now we step into a part of stateful application servers where it becomes more complex. You can't just scale out with a normal application, from Rails, where you have your application tier, which is felt infinitely scalable, since you just have the database you talk to, and you can fire up new application servers if you have big load. With stateful application servers, it's more like you have a big problem, because you can't distribute the state easily, and you have to be very, very cautious to not have a duplicate state somewhere. Imagine it like this. You can, if you're creative, you can simply make yourself a calendar, and each day probably will represent one possible race condition with the state manager. But we have found a magic formula that holds everything together. And remember, we want to do it simple. We don't want to do a complex system. Who of you have heard of Zookeeper? Okay, some. That's good. We didn't choose that, because we thought it can be done simpler. We just take our session ID and do a modulo REST operation with the number of shards. And here you see my Facebook ID, modulo 2. I will land up at the shard with the index 0. And that's very nice, because then we can tell the client, please talk to this shard. And whatever language we use, in whatever step, deployment, landing page, whatever, the language probably has support for modulo. And we are given the session ID, so that's fine. Oh, forgot to mention that there's some one exception, of course. Landing page requests they don't send an ID, or they don't directly go to the correct shard. So we have a requirement here that I just need to tell you that we are doing a static landing page, which figures out the session ID and then directs the user to the correct shard. In order to load balance the whole thing, we're just using DNS round robin, which works out fine so far. As I said, we're stepping into a more difficult part of stateful application servers, and we're also taking trade-offs. Due to the decision we made, simple modal operation to share the state, it's very hard to rebalance the cluster. So rebalancing means that we have to put down the whole cluster, add new machines, and bring them back up again. But we accept that, and we're just trying to plan ahead in kind of Russian style. And could you save questions for afterwards? It's okay? Or it's a very urgent one, which everyone is affected.
Sorry, explain again why you can't add machines.
Oh, okay, yeah. You can't simply add machines because you have to ensure that the number, that this modal operation is fixed. You boot up a new machine, and it knows that it's the right shard because it knows its host, and it knows the actual number of shards which are around at the moment. And to atomically switch this is very complex. You have to switch it in every single instance of the application, may it be a new version or an old version, and you have to switch it in every script and everything that's involved. So having this atomically switched while having it live, we just decided to go for a shut down the cluster and bring it back up again solution, since we don't expect a lot of rebalancing.
Shutting down resets to the session IDs, is that the point?
The session IDs are Facebook IDs, so they're fixed. Yeah. So that brings me to the next point, planning. We just do simple approximations. For example, our time budget, we assume, and it's not correct, is course times shards. Another great example for planning out our load is if an average transaction takes 20 milliseconds with 32 cores per shard and 4 shards, we probably will never afford more than 6,400 transactions. And another example, if 1 million DAU generates a load of 4,000 requests per second, we can take this number, for example, from existing games or approximate this number from our current load data. So, and our most expensive transaction takes 100 milliseconds, but those make only a fourth of all other calls. The maximum for each other call is just 9 milliseconds. So we kind of get a perspective on how performant our system must be and how much servers we have to add or we have to remove from cluster. So now you heard about what we did to basically set up the whole thing, distribute the sessions across multiple shards. Now, another interesting rabbit hole I want to bring you into is our concurrency model. How do you distribute the load from one shard? And basically, this is the question, how do you make programming really adrenaline-fueled and exciting? You could drink coffee. Well, we write multi-threaded code. And we're using threads. That's a very, very simple model. So what is the nature of threads? Threads are not as lightweight as perceived in general, but they're good for keeping them around. So if you use threads, you should avoid spinning them up and down again very often, because spinning up a thread comes with a cost. Also, you should avoid spinning up thousands of threads, because scheduling overhead will probably kill the performance of your application. And I really have to thank the JRuby team at this point, because JRuby makes working with threads really a bliss. We don't have any issues. It's amazing. If you want to look into a very, very good tool set for concurrency, look into Java util concurrent. I really encourage you. I'm a Ruby programmer. I've never programmed Java. But what I found there is really, really amazing. You have atomic value holders. You have fully fledged thread pools with all kinds of flavors. You have queues. You have linked hash maps. You have blocking hash maps. You have a concurrent hash map, which we are using. It's really amazing. So I said, like, it's dangerous to keep many, many threads around. So what are the number of threads we're using in our application? We're using Tomcat as our application server. This has one acceptor thread, accepting connections, forwarding it to the workers. And the application itself has one ticker thread, which is like responsible for session maintenance, shutting down sessions which are no longer active. And one broadcast thread, which is taking care of broadcasting like general information to other shards. How did we make this thing thread safe? This is actually all the code we need to make the access and the creation of sessions thread safe. In this case, we're using concurrent hash map in .self_current, which is initializing it. And the code in .self_get is the code you need to use in order to handle the concurrent hash map with thread safety in mind. So let's step through this. Unless we just get a session from the hash map, we need to create one, of course. But this is the critical part, because we have like 30 other worker threads accessing the session. So we have to kind of make sure that when another thread creates a session, that we have to try to put it back onto the hash map. And this is where putif absent comes in place. Putif absent is a method on concurrent hash map. So if you successfully put your session, you as the thread, into the hash map back again, it will return nil. So you can like happily go forward, continue using the session you just created, the instance. But if not, it will return the session which is in the hash map. So then you can just go on and use that, which another thread created maybe. Then there's another thing you have to make thread safe, which is very important. Access to one session itself. And we are in a golden position here. We don't have to like spread the locks or synchronization blocks around the code. We have found one single place where we can put the lock. Since all the actions a user does, you have to imagine, they're almost sequential. So there's almost no parallelism involved for one single game state or one single session. And that's why we can just simply lock the session access, and this self.with gives us a facility to lock a session. Quite straightforward, easy. We have a mutex instance on each session, which gets carried around, and we just use that. So if another thread comes and I'm just in a with block with my session, he has to wait. Oh yeah, this is another funny topic. Zero downtime deployments. So if you have a stateful application server, it's not that easy, because with Rails, you can simply like spin up application servers up and down. No worries, the database has all the data, and the application servers just talk to it. But if you shut down an application server on our side, we lose sessions. So the idea is keep on rolling forward. Here's our deployment process. It's a lengthy list, and that's what we came up with. We tarball the whole release candidate, including assets and client, rsync that to our shards, spin off a new JVM instance on the next free port. So we have a small route in our Nginx configuration that gives us the current port Nginx is speaking to. And we tell the new instance about the current port so that it knows the existence of a previous instance, wait for a successful response. The JVM takes a while. And then we rewrite the Nginx configuration to point to the new port and reload Nginx configuration, atomic switch, problem solved. Not yet, because then you have a new instance, and the new instance has no sessions. It has an empty heap. And what to do with all those active sessions which are like lying around in the old instance with the old code? So any request which hits the new instance will first ask its own session manager. Do I have a session? No, I don't have one. So it goes further, and if nothing found, it just asks the previous instance. Since on deployment we told it of the existence of the previous instance, I can just make an HTTP call and ask, like, hey, give me that session. I'm the new one now. And if not found there, we just create a new one. But like the if nothing found, ask the previous instance is the most important part, because then you have hot sessions, you can just swap them around. Here's an excerpt of our Nginx configuration. And do you see the pattern here? Probably not if I tell you. The port the current application is serving is 3999, 3999. And we use that to just replace the port with a simple set in place edit. So replace the, I just switched in the slides. It should call port new port, but regardless, we just replace the old port with the new port, and another process watches this file and reloads Nginx. That's it. And another fun fact about our instance lifecycle is it's really hard to determine from the outside what the instance is up to. So it's really hard if you ask one instance, and this instance says, like, I have 3 active sessions, I'm on port this, my previous instance is this, but it probably doesn't know if there's a new instance. So we know there's one state an instance can be in that it can kill itself. So when the first session handover comes in from a new instance, the old instance knows, okay, I will no longer be serving. Since we're in rolling forward mode, I will never serve a request again. So it can just watch its sessions, and when they expire or when everything has been handed over and the instance is emptied out, it can kill itself. That's good. So wrapping it up. I really want to encourage you with this presentation to explore and play around with concurrency. It's not that hard, and it makes a lot of fun too, because we found threads, in our case, is a very good model for parallelizing the load we have. But you should look into processes. What do processes do? You should look into synchronization. You should look into the actor model, and even in technologies like software transactional memory, which is very interesting. They also have different problems, but in this whole universe, you will probably find something that will solve your problem best. And how can you achieve concurrency, simplicity, and productivity with the tools you know today? You know, there's Python around, there's JRuby around. You don't have to write Ruby code that's not threading anymore. You can use threads. It's already there. It's pretty cool. And enable yourself to plan ahead. A plan helps you to stay focused, and it enables way better decision-making. If you just rush into the project, program away, come up with a very fancy edge problem and just code all for that, make yourself a plan, go step by step, and you'll end up with a system where the session manager code is not longer than 20 lines. Thanks. So questions, fire away, please.
So you said when you are rolling forward on releases, the new release knows about the previous one knows the one before it.
Yeah, right. It's a change.
Yeah. Do you happen to have many at the same time? Like you do a release and before the previous one dies, you make another and another. Is it more often just 2 releases concurrent, the old and new one, or are there actually chains of releases that you happen to make?
The question was if there's a long chain of releases during release time or in general. We aim to have not more than 4 instances running at the same time. We benchmark the memory usage of our load, and we can fit in 10,000 sessions in 2 gigabytes of memory. So we can actually keep around a lot. So we're kind of safe in that perspective, but we try to keep it low. So at Wooga in our team, we have weekly releases. So when something goes wrong, we probably have a hot fix and then deploy a new version. Or if we need to fix something during the week, we also roll forward. But at the same time, there's most probably not more than 3 or 4 instances. please.
You mentioned that obviously there's some overhead when you need to make a request to the previous instance to retrieve the session information.
Yeah.
Do you benchmark the overheads involved in that versus making a request to a shared session store? And if you did, what kind of difference did you find?
We just didn't benchmark that. We just went for a solution since it came up to my mind and we programmed it and it was so short and so nice, so we just used it. And so far we're going good with it. But there's a key problem. It's not only that we have this overhead of taking over a request from the previous instance, we also have the overhead of a cold JVM. Nothing is hot, nothing is optimized. So we probably have to find a solution for that in the future.
How do you deal with availability? Like if one instance is down, how do you deal with it?
We start, we just search for the error, maybe, and start up a new one. If something goes down, it's probably like a real harsh problem.
So it's like that you do this module stuff,
Mm-hmm.
find a proper chart based on the Facebook ID, right?
Mm-hmm.
So basically, if you have only 4 instances,
Mm-hmm.
you use like further fork of your...
Right, that's true. That's our fault tolerance plan. So if one machine goes down, SSDs go boom, we probably just lose whatever number of shards we have, like 1/3 of all the users. Or we plan to have like about 8 shards in like peak production, so we probably lose 1/8 of all the users. And since we actively manage our servers, we probably will not have a big downtime for that portion of the users. Yeah, please.
Do you actually store the session objects in some kind of data storage?
No. This is the beautiful thing. Remember the slides with the controllers or the commands we had? It's just Ruby objects. We have a class instance here, class instance there, an array here, and hash there. That's it. And we're just abusing by reference a lot. So there's no copying going on, or no data has to be transferred since it's all in memory already.
Okay, but what if my friend, it's a social game, right? What if my friend is in a different shard? You use this broadcasting.
No, the broadcasting for something different. I can talk with you later. It will for another talk. But if we need data from another shard, we got the ID, so we know which shard it is. We just go there and ask for it. So one HTTP request yields another. This action is very costly, of course, since you have 2 HTTP requests to get the actual data. But we have this broadcast mechanism for generalized user data, which is a Redis on each instance, and it's like updating via UDP. But that's another talk, of course. And but those actions, they happen, but not very frequently. So we are kind of in a good spot there.
There was a question about failure.
Last question, yeah.
Yeah. In case that one node is down, so you lose all data, right?
Not really. We're doing backups, and we evaluate them regularly so that they work. But you have to imagine we're dealing with game data here. So if something really severe happens, the server is being taken down, all the disk is gone, we have a backup we can restore from. And we have hot spares lying around, which can easily, with IP switching, putting them in place again for a completely broken machine. And, I mean, if we lose half a day of data, it's not that important. We are having a comfortable position here. Yeah, it's really nice. Okay, this concludes my talk. Thank you for the questions, and see you around.